Great, thank you. Lucky last of the morning session here. So I'm rather excited to be talking to you about tidal disruptions, something which I imagine is fairly familiar to many of you, not least of all because of this wonderful school that you've had over the last 2 days. I will, however, be talking about it in a context you might not have met before, which is the tidal disruption of gas clouds rather than of stars. I'll also be doing so using some semi-analytic methods, which might also be new to you, and so you might get something mathematical out of this, if nothing else. So, unfortunately, you can't see the title there, but I think that's fine. So, so gas clouds, what do I mean and why should anyone care? Well, as we all know, one of the big open problems in cosmology concerns the nature of the missing mass. That is to say that the inventory of electromagnetically bright material that we can see does not seem to be sufficient in order to explain things like the galactic rotation curves. This is usually interpreted in terms of some kind of non-baryonic dark matter that involves extensions of the standard model. But there are other alternatives that have been explored ever since this problem was recognized, usually involving some kind of cold material, which is also difficult to detect electromagnetically. The canonical example in this category being primordial black holes. But other possibilities is that it could be a non-negligible portion of this locked away in gas clouds, which are cold. And by cold, I mean of the order maybe 10 Kelvin, and thus difficult to detect in infrared and so on. And so this is an interesting possibility to explore. So based on various constraints that come from experiment and theory, things like microlensing and extinction, you can draw a diagram that looks something like this. So this is showing the possibilities of masses and radii which are allowed from various experiments. The diagram really is more constrained than this. In reality, this is just kind of an over-exaggeration to give you a viewpoint. So we're talking about clouds here that have masses maybe a few by 10 to the minus 5 solars with maybe an AU in radius. And so primarily what these would be composed of is an envelope which consists of molecular hydrogen. This will be in various phases, some of which will be condensed. And so you'll have snowflakes in there, hydrogen snowflakes, and hence snow clouds is the name that we give to these types of objects, hypothetically. So in addition to that envelope, there's also the possibility of having a metal core. This is an exciting and attractive option because there's also, in addition to the missing mass problem, there's the so-called missing baryon problem, which is that the metals available that we can see also seems to fall short of that predicted by Big Bang nucleosynthesis, where there are some people here who probably disagree whether that's a real problem or not, but that's a separate point. And so there's a lot really more that could be said about what kinds of cloud models and the hydrostatics and all of this that you can explore here. But for the sake of moving forward, I'm just going to take it as a given that there are such clouds, eventually in the sense that we want to try to put constraints on how they may appear observationally or otherwise. So as I've said, these would be very difficult to detect in isolation, being due to their coldness. However, unlike non-baryonic dark matter, they can have electromagnetic exchanges with stars and can be revealed this way. So the most violent possibility here is that of a tidal disruption. So this is something you've heard a lot about. Essentially, in the event that a star wanders too close within some other compact object within the tidal radius, there's a possibility of a disruption occurring. Much the same can happen here with the cloud and star in a type of interaction. The key astrophysical difference, of course, being that rather than thinking about events happening in the center of the galaxy, this could happen with stray exchanges of just free-floating clouds and field stars, and thus you can essentially have a kind of random population of these things occurring somewhere in the local universe without having to look in a particular place. Unfortunately, these events will be rather dim owing to the energy scales involved, so the kind of fireworks that you might expect would be rather less than that of a traditional TDE. However, astrophysically speaking, the ways in which this might be revealed is through the aftermath of these kinds of events. Essentially, you'll have an expansion, heating, and ionization of the cloud material post-disruption. And this will leave you essentially with a floating plasma screen somewhere throughout the galaxy. And this can be revealed by essentially looking at background objects and this material possibly getting in the way, maybe having an overabundance of electrons in a particular region, something like that, which I'll talk a little bit about towards the end. So positing some quote unquote canonical distributions for the mass and velocity dispersion for these clouds, which are eventually things we would like to actually constrain, we can get a rate estimate for how often this type of thing might occur, shown in the bottom left there. This number is not all that convincing in terms of how often you might expect to see something here. However, as a kind of very extreme assumption, if all of the dark matter density is in the form of these clouds, we can get a number density estimate for how many we might expect per cubic parsec. And thus, over something like a cosmological time, actually, you might expect there to be a non-negligible number of events that are occurring in the local vicinity. And thus, we could try to look for traces for this and then put constraints eventually on possibilities of baryonic alternatives to dark matter. So in order to do this, we're going to apply this semi-analytic method that I hinted at before. This was introduced by Carter and Luminay in the early 80s, a so-called affine model. So again, this is a story where rather an amount can be said, and this scheme is in some sense weaker than full-blown numerical hydro that you might like to do. However, you can get a lot out of this in terms of the description of the bulk morphological or geometric properties of a tidal debris stream. The key assumption at the heart of it is this linearization here that's shown in the sort of middle left equation here, where the idea is you have some kind of ensemble of fluid parcels that represents the cloud or star in that case that they were looking at for the traditional TDEs. And you can map these to some perturbed set of different positions by introducing this so-called deformation matrix. So the idea is that you limit yourself to the possibility of only continuous deformations of the bulk 3D structure. And so you have this 3 by 3 matrix Q that you introduce, which essentially allows for rotations, shears, and most importantly for disruptions, dilations of the 3D structure of the cloud in the way that I'll show you soon. So essentially what you do is rewrite Newton's equations, or if you like, even Einstein's equations in a form that involves this matrix Q. So you have an acceleration here on the left, and on the right is the traditional culprits that you might expect. There's an external force related to tidal forces, which is in the form of this Hessian matrix C. There's another thing which maybe looks a little bit alien, but this is just the hydrostatic pressure rewritten in terms of some kind of canonical variables. And then there's a self-gravity term. So this is describing the ways in which you might expect a deformation to take place, the competition between the tidal forces as well as various other pieces. So I know that's a bit of a blitz. There's a lot more that could be said about that formalism itself, but we can just sort of launch in to see what it can do. So this is a canonical, I guess, again, type of simulation that we can run. I should have mentioned that one of the key values of this that you don't really get out of the possibility from a numerical hydro is that this is computationally efficient. So I can run something like 10,000 different simulations like this just on my local machine in the space of a day. And so we can look at a wide range of different initial conditions that has a lot of value in terms of describing, I guess, bulk statistical properties, which is something we'd like to put constraints on eventually. So what this plot is showing you here is essentially a Z-plane projection onto this 2D screen that you might see in the sky. There's a cloud here shown by these blue ellipsoids that's zooming in from negative infinity on the x-axis. In numerical reality, that's some finite distance, but that's not particularly important. And so I'm showing you here not only the deflection of the trajectory, right? So there's a gravitational deflection of the trajectory in terms of some relative velocities. I've chosen a frame of reference such that the star is glued at the origin here. You can see the cloud is kind of zooming past on this usual typical trajectory, which then gets deflected. The surface, or should I say more precisely, the Z-plane projected surface of the cloud is also shown by these blue ellipsoidal contours. So you can see it starts off as this very happy spherical little thing. As a result of near periastron, this impact parameter of 6AU is sufficiently small such that a relatively violent disruption occurs. And this is showing you the bulk structure of how the cloud evolves. In this particular case, you end up with something that's more pancake-like, where two of the axes are rather large and one is compressed. And so this would appear as some kind of thin film, if you like, which you can learn things about the column density, the rate of expansion, all sorts of other things from the output of the individual sims. So there's many different types of encounters that can happen. By far, the most common is where virtually nothing happens. It's far more likely that you have a large impact parameter than you have a small one. This serves mostly as some kind of a numerical test, but also it's interesting dynamically. So what's going on here is that the numbers are showing you some kind of relative position, which isn't particularly important. The impact parameter I've chosen to run this is sufficiently large that there is no actual disruption that takes place, but there is still a tidal drag that is exerted on the cloud fluid. And as a result of this, there's some superposition of oscillation modes with which it responds, mainly of the pressure restored variety, which we can relate to some kind of analytic things to test the numerical code. There's some angular momentum and twist that's going on here that's encoded through this 3D matrix, and you can see the cloud's kind of breathing. But eventually, astrophysically, that's not altogether that interesting because a cold rotating thing is still just as hard to see as a cold static thing for the most part. We now get into cases when actually something happens. This is a kind of a proper disruption, if you like, but a borderline case. The way in which we actually quantify a disruption is a whole nother ball game, right? You just have some impact parameter and so on. It's not totally obvious what a disruption actually means. Physically, this just means that you should have an expansion in volume out to infinity, but numerically, this can be quite a tricky thing to actually capture. This can be quantified with an internal energy criterion through the Hamiltonian analysis, which I won't really bore you with. But the key point is it's this kind of energy scalar that we can introduce that has various terms in it related to self-gravity, and pressure. And depending on which of these wins out and the sign of this scalar, you can talk about the material being either bound or unbound, right? Which of these is winning. So in this case, we have a relatively moderate impact parameter, and instead we get a more cigar-like configuration where two of the axes are expanding. One of the axes is expanding and two of the others are remaining virtually stagnant. And so in this case, you end up with a more cylindrical-like configuration or something which is cigar-like. This highlights, I guess, one of the limitations of this affine model. We don't have break-off of material. This deformation is assumed to be continuous. And so we miss some critical things like tidal tails and fallback accretion, but we can still track the bulk center of mass properties that we might expect of the stream. So punchline is that, as I've said, the advantage of this is we can run many, many different types of simulations in a relatively short time. We can build a diagram that's something like this on the top right. What this is showing is this energy scalar that I introduced. Each individual pixel here is an individual simulation. There's about 11,000 that constitute this diagram. I've drawn in a big, thick red line where the boundary between positive and negative energy lies, essentially telling you where the disruption is occurring. We can then focus our attention only on that subsection of the diagram where there is a genuine secular expansion in volume, and now start trying to talk about statistical properties of this stream. This has a number of things we can then learn from this. For example, the expansion rate and the velocity tell you something about how long you might expect the disrupted cloud to last within a given patch of sky. And the density evolution in the other direction tells you about the column density, and this is essentially how much of an effect you might expect to see. Right, so the thing is continuously expanding with the density dropping. Eventually, you get to the point where this is being subsumed by the ambient interstellar medium, contributing in that way. However, in the interim, you might be able to see something interesting. So there's rather an amount of different statistics we can do here with this simulation library that we've constructed. One of the examples is to look at the possible different types of axis ratio. So in general, these cloud post-disruption are some kind of complicated triaxial ellipsoid, but we can describe them in a kind of bulk way in talking about these 2D projections in terms of this axis ratio. This is telling you, length versus width, how wide is the thing versus how tall it is. This will tell you something about how this might appear to an observer that you can eventually try to look for. And so we can make a diagram, something like here on the left, assuming some different priors for the star and cloud distribution. So this is the cumulative distribution function, and this axis ratio depending on where you are in the galaxy, in the thick disk, thin disk, or in the halo. You can draw some predictions like this about what essentially expectations you might have here that again connects to these various other bits and pieces. So this is my last slide here. There's rather an amount that can be talked about. I have kind of skipped over some of the details and given you a bit of a blitz here, hopefully to excite you about tidal disruptions with things that aren't just stars and compact objects. So I mentioned earlier, one of the astrophysical ways that these might reveal themselves is by getting in the way of some other background source you would like to see. Good examples of this are radio sources like radio pulsars and quasars that's shining and you're looking at them. One of these disrupted tidal streams gets in the way, acts as some kind of scintillation filament. This might be responsible for some things like scintillation arcs or various other things where you might have overdensities of electrons, which are otherwise difficult to explain. And based on the prevalence of those that we can look for with surveys, you can try to put constraints on the possibilities of baryonic alternatives to dark matter. All right, thank you.